Okay, this is our first lesson of the ionic and covalent bonding unit. There's only, I think, 4 days with this unit, but the concept is pretty simple. You probably have been exposed to this in middle school. So basically, we're just going to learn how to draw the molecules. We're going to learn Lewis dot structures, and we're going to discuss valence electrons and how the molecules and atoms bond together. Okay, so by the end of this lesson, though, we're going to be able to explain how ionic and covalent bonding occurs. We're going to be able to draw diagrams for elements, but only in the S&P blocks. And we're going to determine the valence electrons. So we already know how to do that last bullet point, but we'll go ahead and just discuss it briefly. So the two types of bondings, you have heard these words in class when we talked about formula units and molecules. But ionic bonding just involves a transfer of electrons. I know in class I didn't really talk about transferring electrons or how it's bonding, but I told you that it's basically a metal bonded with a non-metal, and that's ionic bonding. So they're transferring electrons. So one element's losing it and one is gaining it. So an example of this would be like sodium chloride. And covalent bonding, that involves sharing electrons. So the atoms will share to become stable. They're not like transferring the electron. And this kind of bonding we have discussed in classes between two nonmetals. Okay, so there's an octet rule, and that states that the atoms will gain or lose enough electrons to be isoelectronic with a noble gas. Again, we have discussed this in class. The whole reason these ions become, or these atoms become ions and gain their charges or lose charges or whatever, is so that they can be as stable as a noble gas. So they're all going to try to get 8 valence electrons. Obviously, except for hydrogen and helium, they're going to have 2 valence electrons in their shell, their outer shell. Okay, so they're going to have 1 dot on each. They're going to have 2 dots on their outer shell. If you remember, the first shell in a hydrogen or the first shell of any element can only hold 2 electrons because there's only an s orbital there. So that's why these two can only have 2 electrons. So the electron dot structures. So there's a certain way you need to fill them in. My college professor taught me to go up here, 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 and here. You're going to fill in dots for the valence electrons up to 8. But honestly, you just don't want them to be like clumped side to side and side here, and then these be empty. So one good way to do it is you can do your first electron here, which is a dot. Your second one will go here, third here, fourth here, then fifth, sixth, seventh, eighth. It's just best to have one on each side. Actually, it's our rule. You have to have one on each side before you go ahead and fill the second one. Okay. So the number of valence electrons are determined by the group the elements are in. And we've kind of discussed this. So group 1 on the periodic table, they will have 1 valence electron. Group 2 will have 2, okay? And then we skip the whole transition metal block, the D block, and then we go to 13 where boron starts, and that has 3 electrons, 4 valence electrons, 5, 6, 7, and 8 valence electrons, okay? That's the pattern on the periodic table. The electron dot structure, so we'll see with lithium, okay, that is, other than hydrogen, that's the first one on the first group, so they all will have 1 valence electron all the way down the periodic table. All the way down the group on the periodic table, so lithium, sodium, and potassium will all have 1 valence electron. And then these guys will have 2 valence electrons, okay? Number 13 will have 3 valence electrons, and so on, okay? All the way up to 8. This is what all of the noble gases look like. Now, keep in mind, we'll talk about that in a minute. So valence electrons, they determine how reactive they will be. So remember when we talked about, on the periodic table, we talked about elements going down the group will all kind of react similarly. And then elements going across a period will have the same number of energy levels. So this is what they're talking about here. They behave the same. That's how they're reacting. They're reacting the same. So all the elements in the first group, so like lithium, sodium, potassium, they will all act very similar to each other. And same for group 2. They're all going to lose 2 electrons. 13, they'll lose 3. 14 will gain or lose 4. Okay, it depends on what they're doing, who they're bonding with. And 15 will gain 3, gain 2, gain 1, and then of course noble gases do nothing because they're already happy. So we've already talked about the charges as well. So group 1 will have a +1 charge, group 2 will have a +2 charge, group 3 will have a +3 charge, group 4 will have plus or minus, and we've already talked about these, okay? So this is just the same trend we've talked about all year. We're just learning it officially now. So yeah. So electron configurations for ions. This is something you guys already know, okay? And we've even determined valence electrons for the outer shell. So for example, valence electrons, you have the outer shell, which is number 2 here, and number 2. So that's the highest energy level. That means it's the most outer shell. So then you're going to add the electrons on these on these energy levels. So that's 6 plus 2. So neon will have 8 electrons in its outer shell. Magnesium with a 2+ charge also has 8 electrons in the outer shell. And same for this one. So remember how this was on our electron configuration test. Phosphorus will actually gain 3 electrons, becoming isoelectronic with argon. So that means it will have 8 valence electrons. So in the outer shell, which is 3, okay, 6, 7, 8 electrons in this outer shell. Okay, moving on. Here are some characteristics for ionic bonding. Okay, so ionic bond will have a positive and a negative ion bonded together. That's a metal and a non-metal. Okay, they will make crystals. So ionic compound is made up of crystals. So that would be like your salt crystals, and even the copper chloride, pretty blue ones that Jai-Ho made for us. Those are crystals. So they're made up with a metal, the copper, and a non-metal, which is chloride. Okay, and moving on. A crystal is just a 3D repeating pattern. So that thing right here at the bottom, that's a crystal. It's just for example, NaCl. The little one right here would be chlorine, and the big one would be sodium. And it's just repeating NaCl into a crystal formation, and that's what you see when many of them bond together like that. That's what you're actually looking at. Okay, and then a formula unit is the lowest number ratio of ions. So it could be, I'm just making this up, but if it was Na2Cl2, the formula unit of that would just be NaCl. Okay, it's just the lowest whole number ratio. Okay, and then ionic compounds tend to have high melting points, and they conduct electricity when melted or dissolved. So when you put salt in water, it tends to conduct electricity pretty well. And we will actually have a lab over that, electrical conductivity of different ionic solutions. So we'll actually get to see this in the lab. I don't have any plans on melting any of them, but we'll see. So keep in mind everything that we just discussed. It's very black and white. If you plan on becoming a chemist or you plan on going to IB, you're going to learn that there's actually gray areas. And like I've been telling you all year, it's not always just ionic or just covalent bonding. It will also, it's more like a transition from ionic to covalent. And we're going to learn the word polar and polarity in one of the lessons coming up.